Today we're going to study the magnetic field of the solenoid. So first we draw a solenoid. Okay, so it's just a wire that's kind of made this way. Usually these loops are closer to each other. They even touch each other. But usually this wire is covered with a film or enamel, so it becomes so when the loop touch each other, the current doesn't go sideways. The current goes only through the wire inside. Now this is a solenoid. So this current here that's going in the wire is going to generate a B field inside the solenoid. It will generate a B field outside the solenoid, but that B field is weak. I will explain why. First, we need to follow this current. Let's see, the current comes out here, and then it goes in here. Because it's looping, comes out here, goes in here. So you can see, it goes in here. We can keep going all the way to here. Comes out here, go in here. Now, we need to find the magnetic field inside here, inside the solenoid. You see, the current at the top is coming up. At this location is coming up. So I'm gonna use my thumb rule. Here is my thumb. I grab the loop and look at my thumb is pointing up. Why? Because the current is pointing up at the top. And look at my fingers inside the solenoid. If you look at my fingers, they're going to the right. So the B field will be going like that, to the right. Now, from the bottom sections of the wires, these bottom sections, we can also use the thumb rule. So the current is going down. So here is my thumb. I flip my thumb so the thumb is going down. And look at my fingers. You see they're going to the right. So these bottom sections of the wire will generate B field going like that. You know? Now, this B field is going to be strong inside the loop, but it's going to be weak on the outside. Why weak? If we look at the B field generated by the top sections of the loop, my thumb is going up. Look at my fingers. They're going to the left. So the B field here is going like that due to these top sections. So I call it like B top due to the top sections. If you look at the wires at the bottom, my thumb will follow the current at the bottom, and look at my fingers, they're going to the right. So you have, this is B bottom, okay, this section. Now this B field almost cancel that B field. The B field due to these top sections of the wire, of the loops, almost cancel the bottom sections. The reason it doesn't cancel them completely, cancel the B field completely, is because this group here of wires, they're actually far away compared to this group here at the top, far away with respect to the distance here. You see, these wires here compared to the distance, this distance from here to the wires at the bottom is bigger compared to the distance from the wire at the top to that location. So that's why you have some left over. But this B field here at the top is weak. And here in the side is strong. Because inside it adds up, but outside they cancel, almost cancel. You see? Like that. Now, for us to find this B field inside, we need to use Amperes law. So let me make a bigger loop like this. And then, and just look at these sections here. These are the currents coming out at this section and going in here. Here is the current I. So the Ampere loop will be some loop that will go around these portions of the wire. 1, 2, 3, 4, 5. And now we write our equation. The integral of B dl is equal to mu 0 times I enclosed. I enclosed is the current that's inside this Ampere loop. This is called Ampere loop. Ampere loop. This one here. Now, let's study the right section first. I enclosed, we have how many currents? 1, 2, 3, 4, 5. So we have 5. But we need to be general, so instead of putting 5, we put N. So this I enclosed is equal to mu 0, is equal to N times I. Here, for N is 5 for here, but in general, we just put N. So now our equation changes. So I put here B dl is equal to mu 0 N I. Now we want to find, we found the right section. You see here, it's easy. Mu 0, constant, and the number of loops, I, the current in the wire. Now we need to look at the left section. We have this dot product. We know that B dl is equal to B dl cosine theta. And the angle theta is between the vector B and vector dl. Now, this loop here, we can cut it into 4 sections. So we have this section here, this one, this one, this one. So we have 4 sections. We can call this one DL1, this one DL2, this one DL3, this section here, and this one here DL4. So we have this section 1, 2, 3, 4. Now we come here and write B dl is equal to B, and then I have dl1 plus dl2 plus dl3 plus dl4. So I have 4 of them, 1, 2, 3, 4. Now I put here B dl is equal to B dot dl1 plus B dot dl2 plus B dot dl3 plus B dot dl4. 1, 2, 3, 4. And we look at each one. Let's look at this first one here. Here is dl1 is vertical. The B field is going like that. We discussed it here. The B field is going this way. You can see that B dot dl is 0 because we have cosine pi over 2 is 0. You see this B here is perpendicular to dl1. So the dot product B dl1 is 0. So this is equal to 0. So we have 0. Let's look at B dl2. Look at the B field is going to the right. Look at DL2. DL2 is going to the right. So you see they're parallel. So the angle between them is 0. So I put cosine 0 is 1. So I put here B, D, L2. This one will survive. You see, the B field is going to the right, and the L2 going to the right. They're parallel. So cosine 0 is 1. So I have BDL2 survives. Let's go to BDL3. B is going this way. Look at DL3. It's going vertical. See? There is 90 degrees between them. So this is 0. Because here we have B is perpendicular to DL3. And here B is perpendicular to DL1. So that's why I have these 0. So this guy survived. These two are 0. Let's look at the last one. I just explained to you here that the B field in this section, they almost cancel out. You can see here, this B top is going to the left, B bottom going to the right, so they almost cancel out. So you have a little bit of B field left over. So the B field on the outside is so weak that we just ignore it. So I put here weak field. Now, what do we have left? BDL2. And this DL2 is the length of the wire. So I just put here BL. This is the length of the wire, or the length of the solenoid, not the wire, the solenoid. This is L. From here to there. DL2 is from here to there. So DL2 is L are the same. Look now on the left side. I have BL. Now, if you go to the integral here, the B field is constant. Okay? If you, let's say you try to find the B field here, there. That B field is constant. Okay? Because is coming, you have the contribution from this, and the distances are constant. This distance here, this one, that one. These distances are constant. So the B field on this line is constant. So when you try to integrate, this B constant comes out. And then you just have B dl is equal to mu 0 n I. The integral of dl is just L. So you get B L mu 0 n I. Now the B field is equal to mu 0 n I over L. But this n over L we have here, am I right? N over L, that's number density. We call it small n. So here we can write B is equal mu 0 n, this one, times L. And here is the B field inside the solenoid. Okay? So I put here field inside solenoid. Okay? The B field inside there. Or here. Inside. So now if you want a B field, you don't have to have a magnet. You can just have a current and a wire. So somebody would say, I can generate a B field with a magnet. You have north-south. Somebody would say, why have a magnet? I can just have a solenoid. So the B field will come out of the north. Same thing here. Now these magnets, you might not have permanent magnet. There are not as many available or at your own choice. But here you can choose the B field that you want. You just by changing the current. I forgot here, I put L. I'm sorry, I made a mistake. I have to put I here. I'm glad I discussed this is the current I, because look, I have N over L is small n, put small n, and this is I. So this is the equation, mu 0 times small n times I. So if you make the current big, then the B field becomes big. If you put so many loops, this n is big, then the magnetic field becomes big. So you can control it. You can choose any magnetic field you want depending on the current and the number of loops. Okay, see you, have a good day.